Hi everyone, in this video I will build 2,2-dimethoxypropane using the Snatoms kit. We will identify functional groups, hybridization, and molecular geometries. When we use the Snatoms kit, hydrogen will be represented by the white ball, carbon will be the black ball, and oxygen will be the red ball. The molecule that we are investigating is C5H12O2. This is 2,2-dimethoxypropane. This means we're going to be using 5 carbons, 2 oxygens, and 12 hydrogens. The first thing we notice is that the last word in the molecule represents how many carbons are in the main chain of the molecule. Propane indicates that there are 3 carbons bonded in the main chain. Let's start by building our first methyl group. A carbon is going to want 4 bonds. These bonds are overlapping electron orbitals. Hydrogen atoms will be attracted to the carbon atom and will form these overlapping orbitals. Once 3 hydrogens have bonded to the carbon, another carbon atom will attach to the methyl group to form the 4th bond. For now, we are going to attach 2 hydrogens to the central carbon, making a methylene group. After 2 hydrogens are attached, another carbon atom will be bonded to the central carbon to complete all 4 bonds. Because we know there are only 3 carbons in the main chain, this means that 3 more hydrogens have to be attached to that 3rd carbon to fulfill its bond requirements. Now we are going to build upon our main carbon chain. Currently, we have 3 carbons and 8 hydrogens, but we're missing 2 oxygens and 2 carbons. So we have to figure out where oxygen and where carbon are attached on the molecule. Let's turn to the nomenclature. Meth and oxy means that there will be a CH3 and an oxygen group. Di means that there will be 2 of them. The numbers 2,2 means that both oxygens are attached to carbon number 2 on the main chain. 2 is determined by counting the carbons on the main chain. Counting from left to right, we're going to count 1, 2, 3, and the other way would be 1, 2, 3. This means that the central carbon will be carbon number 2. Because 2 substituents need to be added to the central carbon, we are going to take away those 2 hydrogens we have added before. This forms a quaternary carbon group, which is just a carbon with no hydrogens attached to it. Now we are going to add the oxygen groups. Both oxygens are going to form bonds with carbon number 2. These oxygens are considered substituents, which is an atom or group other than hydrogen on a molecule. Now that the oxygen requirement is satisfied, we still need 2 more carbons and 6 more hydrogens. 2 methyl groups, which is a carbon bearing 3 hydrogens, will be attached to each oxygen group. Oxygen only requires 2 bonds to be stable. In this molecule, both oxygens are bonded to a quaternary carbon and a methyl group. It also possesses 2 lone pairs of electrons, which help stabilize its structure. This is our final structure. We have 5 carbons, 2 oxygens, and 12 hydrogens. Now, let's identify the functional groups in this molecule. Both oxygens form an ether group. An ether group is an oxygen that is bonded to 2 separate carbons through sigma bonding. An alkane functional group can be found in the main carbon chain. An alkane is 2 or more carbons that are bonded to each other through single bonds. Each carbon and oxygen atom will have a sp3 hybridization. sp3 hybridization occurs when an s orbital and a 3-part p orbital merge. The electrons present through bonding in a molecule will then inhabit each orbital. Each valence electron will then inhabit either the 2s orbital, the 2px, 2py, or 2pz orbital. Now that we know all orbitals are sp3 hybridized, let's go over the molecular geometries present in this molecule. All carbons exhibit tetrahedral molecular geometry. This is indicated by the central atom with 4 bonds, all of which are sp3 hybridized and no lone pairs are present. What ends up happening is one atom sticks towards you, another sticks towards the back, and the other are in the linear plane. The bond angles for tetrahedral geometry is 109.5 degrees. The 2 COC bonds are bent. This is because out of its 6 valence electrons, oxygen only forms 2 bonds, leaving 2 sets of unpaired electrons. The unpaired electrons cause the COC bond to bend because the lone pairs push the attached carbons down. This has a molecular angle of a little less than 120 degrees because it's not quite linear.